So build status update for the character generation board, character screen generation board, the 6264 and the 6116. So I think that's the 6116 there, and the 6264 is over here. They both arrived nice and quickly thanks to Mouser. So I've put them in their respective sockets, and what we should expect to see now when I turn it on, haven't tried this yet, is that we should see a character screen with some random, memory pattern characters, but also if we can spot any duplicate characters, then maybe there will be some characters with different palette entries. Although the palette is also random memory pattern initialized, so or pseudo random. So I don't know what we'll quite see, but what we should see is that we should see a recognizable character screen of approximately 32 by 32 characters, give or take a few lines, because the screen is not entirely visible. There's the top and bottom borders for 16 by 16 pixel sprites, and I think if I remember rightly, the addressing as well doesn't quite start for this. The addressing for the screen and the character and color memory doesn't quite start from the very first address, which is 9000 in hex. I think it's 9040 was the first top left hand corner character that could be visible in the hardware simulation. So anyway, we'll see. Let's turn it on, and hopefully it will still work. And yeah, no blue smoke or magic smoke will occur, hopefully. Let's turn it on. We have a good sync signal from the video conversion board, and magic. Isn't that fantastic? That's just great. So green is the predominant color, but we can see that we have distinct characters, and depending on the palette entries, because I think if I remember rightly, the bottom 4 bits of the palette of the character, the bottom 4 bits of the character color RAM, which starts at 9400 in hex, that contains the palette entry, and then the next 2 bits contain the upper high bits of the character index, and then the next 2 bits are horizontal or vertical and horizontal character cell flips. This hardware is really nice, is that it's got horizontal and vertical flipping for free, basically. Well, it's not for free, it uses extra logic, but it's just inversion of the lines, the lower lines, and the barrel shifters and everything, which was all explained in a very, very long video where I took us through the schematic, the full schematic, and how all of the flipping and the shifting worked. But yeah, so this is great. This is working again, first time. Fantastic. It's working really well. So a really good test would be now, because I've enabled the RAM or socketed the RAM for all 3 bit planes for the characters, is that depending on the data, some of these pixels are going to be transparent for the character screen, and they should show the next pixels down. Now the next pixels down are all floating at the moment. Yes, so I've put a little wire in here already. So if I go down here, you can see that the character and the palette lines are all connected up. And for the character screen pixel header, now this header here is the next layer down. Traditionally this would be the sprites, but I don't have the sprites board at the moment. I was seeing if the rest of this worked first, and it does. So I'm going to be building the sprites board at some particular point after I order it. So anyway, if I tweak what would be the sprites pixel in the second layer, and it should alter the pixel that's transparent. If there are any transparent pixels here, then we should see those discretely flashing on and off when I tweak the value here. So if I connect it to ground, oh, there we go, boink. So that's me tweaking the second plane pixel only, and it's flashing on and off. So there's me grounding it to logic 0, and then there's me let it float up. So later on, if I analyze these video signals, I'll be able to see which pixels from which characters are consistently transparent, and to validate that all that's working. But it does seem to be okay. Basically, it's like replacing one of the colors, which should be a transparent color, with all of the same color. Okay, great, fantastic. This works really well. I'm really very pleased with that. So, as you can see, it's a big mess of wires. So my next stage is to create a shorter board interconnect cable for this. Also to create a board interconnect cable for the power, but also the memory address and data bus, which is what this 34-way here is. Basically, you know, it's data down this side and 16-bit address up this side. So 34-way interconnect here. After I do that, then all of these, you know, debug wires basically disappear. And then what I'll be able to do is that I will be able to then start creating I'll do it on a breadboard first of all, I think. So I'll be using, excuse me for a second, these. I will be using these. I don't know if you can see them clearly. I'll put them down here, and I'll let there we go. So these are Commodore 64 user port connectors, and I will be soldering up one of these with some nice decent wires here. I'll be bunging it into a breadboard, not this one, this one, into this breadboard. I will then hook up this to the Commodore 64, and I will create a very, very simple, non-optimal 8-bit data from the user port to 24-bit data expansion, probably 24-bit data plus another few bits for memory write control and stuff like that. So it's going to be a very non-optimal, very slow 24-bit data bus with 8 bits of data, and that's just going to flow straight into here, into this header, into the extended memory bus header here, and that will enable me to control in a very, very slow way by poking output 8 bits from the Commodore 64 user port into here. And then I'm going to start creating a Commodore 64 program which will upload character data, upload palette data, and upload character screen, color screen information. And then we should be able to get this animating as expected. Now, I may, if I have time, if there's enough free space on the breadboard for that complexity, to allow the Commodore 64 to read the VSync. So this board here, via this header here, the video 1 header down here, generates a nice VSync and also HSync signal, but the VSync on low. So that will enable me to then synchronize the graphics updates from the Commodore 64 and hopefully give me enough time to reset the extended memory bus so that I can time writes to this RAM during the VBlank period, so then we won't get flickers. Because at the moment, if I try and write to the screen memory, for example, while the screen is being displayed as it's tracing down, and this is what we get on the screen, is that we get bus contention, and obviously this is probably the character FF, 2FF, the character 3FF, probably, because that's basically bus contention, and that's probably coming out logic high. So we don't want to update the character screen contents as it's displaying. So that's why I want the VSync detection in there too. But yeah, cool, very nice. So yeah, tidy up this board with the interconnects. Remove all of the debug wiring, which is asserting all of the memory addresses and data buses, and then start connecting up to Commodore 64 user port and getting that to work. The Commodore 64 user port, I will, as a prototype on the breadboard, I will use the logic analyzer to make sure that the signals are correct first and expected, and then it should just be a very simple case of connecting the output signals straight into these headers here, and then just repeating the test from Commodore 64 that was verified by the logic analyzer, and then just seeing everything work as expected. So happy days. No real major gotchas so far. I'm really very, very surprised to have got to this point in time. So slight change of plan. I decided to sandwich the boards together with their headers because now that I've fully tested the RAMs and everything on the character generation board, then I don't need to have any more debugging capability right now. So for the best connection, they're all sandwiched together like this now. And this is an interesting screen. I just wanted to show you. This is where I just connect OC0 to OC3 on the layer 1 pixel input header here. And what we're viewing here is that we are showing the contents of the color RAM memory. There's no pixels being input to the pixel layer 1 input header, so we're just seeing whatever is in the color RAM, which is exactly what I'm expecting to see. So now when I connect up the pixels, I'm expecting to see pixel data as well. To make it a little bit more maintainable, I'm now using these wires here because they're a lot better than using these just purple wires which don't have any color coding to them really. So it's looking a lot neater now. And now, with all of the pixel lines connected and also the memory bus detection header connected, now we have a nice blue screen at the moment. This is lucky. The memory just happened to fill with this pattern, so it's all connected up now. Now it's just waiting for me to add the Commodore 64 8-bit user port to 24-bit bus interface here, and then we're all ready to go. Actually, here as well. But cool, it all works and it's all stable. I can fiddle with the wires and everything, and nothing wrong goes and nothing wrong happens. So great. Now to continue on. Oh, and also tidy up the desk because I don't need to be in development mode anymore. I need to be in mostly software mode, which is cool. Does look nice though. Yeah. I need to get spaces. Now, the next revision of this board. Oh yes, so things to note for next revision. Thing number 1 is these pixel headers here need to have the same arrangement of input lines as the pixel header on each of the boards here. At the moment, really annoyingly, they are reversed, which makes it really silly for connecting these up. The other thing to note, oh yes, okay, so while on this board having nice vertical interconnects like this seems to work really quite well. If the board is multi-layer, I don't think this approach is going to work very well. I think it's going to put quite a lot of strain on here, and it restricts the configuration of how the boards can be put together. So I think in the next revision it's going to be better to change these to be right-angled IDC connectors, and then I can just have a ribbon cable going down for the bus. I think that's going to be a much better arrangement. Perhaps likewise for this one too, also a right-angled connector, something which is probably more like just a VGA output, which would be ideal, I think, because then I don't need to have all of this wiring loom here. I can just have a VGA output connector. So yes, that's thing number 3. Thing number 4, spacers. Perhaps. Although if these are right-angled IDC connectors, then I don't really need to have board spacers per se. Although, still, if I want to stack these boards, then it would be nice to have spacers. So, spacers. Another thing is power supply. So I need to really have a proper power supply. That's been noted before, but I'm just noting it again in this list. So the input for the video board, I think, should be obviously the primary controlling input for the memory bus, the extended bus, the 16-bit normal kind of a bus, and then the data lines too. So what I think I'll do is that I'll have the right-angled IDC connectors for the interboard connects, but I will also have input headers for the top end of the memory bus, perhaps, or just continue the ribbon cable upwards. That would also be one thing to consider. So, because for ease of debugging, it's great to be able to whack these wires into the top of these headers here, and debugging is important. However, for interconnect stability, it's going to be better to have, I think, the right-angled IDC connectors. Maybe a hybrid combination for the next generation of the board. We'll see. Anyway, it's working really well so far. So now, time to get the Commodore 64 to start poking memory into this thing. Data into the memory, rather. A little bit of progress with just enabling me to debug the memory interface a little bit more easily. I've just set up a couple of switches here on the breadboard. This one here is for the extended memory bus, bit 0, which is the least significant bit, which is 1. So this corresponds to all of the memory addresses up there. So where it says expansion bus 3, where it has 0, 1, down here, this activates any of these addresses here, depending on what's on the input address bus here. So what I've set up here currently is 9040. 9040 should be the top left-hand corner of this screen. Strangely enough, the first 2 lines in the RAM are actually, although they're connected up in the schematic, they're not actually output because there's a top and bottom border. So anyway, 9040 in hex should be the top left-hand corner of the screen. If I press this switch here, this one here, this button rather, if I press this button here, currently at the moment it's low, but if I press it now, it goes high on the extended memory bus. And what that means is that the internal chip logic, when the screen does this, it means that there's contention, and it means that it's actually outputting probably character FF or 3FF, because all of the lines are in contention, therefore it reads as high. And what this means is that when I press that button there, the screen just displays all of the same character because it's the contention character. So what we have now, what I'm going to do is that if you notice the top left-hand character of the screen, I'll zoom in a little bit here, the top left-hand character in the screen is the same as the character which is output during contention, which indicates to me very strongly that it's 3FF in palette memory. Okay, the top 8x8 pixels do not change when I flip between contention screen and normal character screen. Okay, because when I enable this address, I want to start being able to write to this address. So basically the memory is in contention with the video reads for the character screen display. So it just displays this character instead. So what I've done is that I've set up on the data bus here a character which is different to 3FF. Because the data bus is 8 bits wide, this is actually FFE, floating high, apart from this one, which is bit 0, which is floating low. So currently, at the moment, my voltage supply is overheating. So I'm going to have to wait for it to cool down a little bit. You can see that the LED is flipping on and off. Hold on. One moment. So here we are again with a different screen. Now I've cooled down the voltage supply. So what I'm going to do is that I've set up the data bus to be FFE character, so 3FFE. So at the moment the character is the same as the contention. If I then press the other button, which brings the memory enable write line low, now it's written a different character to the top left. So you can see when I switch between the contention 3FF and now it's showing 3FE because the character up in the top left hand corner of the screen has changed. So that indicates to me that the memory writing logic, at least for that location, 9040 is actually working correctly. So I've got a lot more confidence now in being able to connect this up to an external data source, which will then allow me to do a lot more programming on this, and then we'll see how that goes. But obviously I still need to do something about this power supply because it's definitely not up to standard.